Welcome to 28th lecture of graph theory. In the last class, we were discussing about a special kind of intersection graphs, namely the intersection graphs of axis parallel rectangles on the plane. So, these were again considered as a generalization of interval graphs, because axis parallel rectangles can be seen as some kind of two dimensional rectangles, because an interval so it is a two dimensional intervals, because an interval is like this. So, if you had two dimensions and if you consider an interval here and an interval here, so a combined effect is this rectangle, right. Because when you take the Cartesian product, we see this thing. So, in other words, this rectangle's projection is this interval, this rectangle's projection is in this interval. So, in that sense, these are kind of two dimensional intervals. So, that way we can think that this is a generalization of interval graphs. We had considered several other generalizations of interval graphs earlier, like circular arc graphs, when the intervals are considered on the circumference of a circle rather than on the straight real line, and AT free graphs which try to capture the linear structure of interval graph by identifying that it is that ATs, the absence of ATs are the reason for that, alright, how generalized to a much general structure called AT free graphs. Chordal graphs, where we identified that interval graphs are graphs without chordless 4 cycles, and then we defined the superclass chordal graphs which contains the interval graphs. So, there are several such generalizations. Here is a obvious generalization where instead of considering the intersection graph of the intervals on the real line, we would rather consider axis parallel rectangles on the plane and then consider the intersection graph. And in the last class, we had also seen that, so there are graphs like cycles and all big cycles which can be represented as the intersection graph of axis parallel rectangles, but which cannot be represented as the as an interval graph, right. They are not interval graphs, right. For instance, the cycles are examples. So, and then we ask this question, is it possible to represent any graph as the intersection graph of two dimensional rectangles, so axis parallel rectangles? It is not possible also, because we told that there is this graph. We promised that there will be a graph which is drawn like this, 3 vertices, and if it is, so okay, I will 3 vertices. So, this kind of a rectangle. See, this graph cannot be represented as the intersection graph of axis parallel. Today we will explain why it is so, and to understand this, we want to understand how to analyze these rectangle graphs as the intersection graph of two interval graphs. We had shown that if you get a rectangle representation, I mean if you get a graph and somebody gave us a representation of the graph as the intersection graph of axis parallel rectangles, what we can do is we can project each rectangle to x axis, and if you take the intersection graph of the intervals corresponding to these projections, we will get an interval super graph of the given graph. Hence, I1 Ix, which is a super graph of the given graph, right. The same vertex set, but the edge set can be more. Similarly, if you do the projection on the y axis and take the interval graph resulting from the projections, then that will also be a super graph of the given graph, right. That will also be a super graph of the given graph. So, here the vertex set is same, but the edge set can be more, but every intersection here will correspond to an intersection for the projections also, but sometimes you may get an intersection even when the rectangles are not intersecting. For instance, if you had a rectangle here and then if you project it here and it here, both of them are intersecting in the projection in the y axis, but they are not actually intersecting, right. That is why these extra edges are coming. But the crucial property is that if you take the intersection of these two interval graph that we created, that means Ix intersection Iy. When I say Ix intersection Iy, I mean the intersection of the edge set. We will get back the edge set of the original graph, because it is not possible for two non-intersecting rectangles to have intersection in both their projections, because if both their projections have intersections, the rectangles have to intersect, because after all these are Cartesian product of this thing, right, the projections. So, we can see that if we have a representation in terms of the rectangles, then we can find two interval graphs such that G is the intersection of these two things. So, the point here we told that now that particular graph we considered, right. So, this graph, this has three missing edges, and if this is represented as the intersection of two interval graphs Ix and Iy, then this should go away in Ix or Iy, this should go away in Ix or Iy, this is also should go away in Ix or Iy. So, that means because there are two interval graphs and three of these missing edges, absent edges should disappear in one of them. So, we applied the pigeonhole principle and told that there should be one of these cases, maybe Ix, in which two of them is, say, let us say this and this is missing. That told us that it will create so it will create a 4 cycle for us. This kind of a 4 cycle will come from that. So, this is the 4 cycle in the interval graph, but in the interval graph we cannot have a 4 cycle, and then that is where the contradiction came. So, this was a simple argument to show that there are graphs which cannot be represented as the intersection graph of axis parallel rectangles. It is a simple enough graph. So, we have a small clique here on 3 vertices and we have a small clique here on 3 vertices, and we connect it except this matching, right. So, like this, right, except this perfect matching between them. Now, we can generalize this concept further. We can ask, what if I consider the intersection graph of axis parallel boxes in 3 dimension. So, why 2 dimension, we can go to 3 dimension, right. So, then so of course, we can it is a super class now. So, it can capture all the rectangle graphs, the intersection graph of rectangles on the plane, but then it can capture more. For instance, this can be represented. So, and now we will ask whether it is possible to have graphs which cannot be represented as the intersection graph of axis parallel cubes in 3 dimension. It so happens that there are still graphs which cannot be. So, it gives us 2 questions. Suppose I go to next dimension now, 4th dimension. Can I do it here? So, given a graph n, is it possible to represent it as the intersection graph of axis parallel rectangles in some dimension, some finite dimension? So, this is the first question which comes to mind. The second question is, in that case, is there a, what is this best value of that, right. So, it is the smallest value of that. So, the first I will show that it can be done on some dimension. So, this is done by Fred Roberts in the 1960s. He showed that any graph on n vertices can be represented as the intersection graph of some axis parallel boxes in some n by 2 dimension. So, we will not get to the details of n by 2 dimension. I will show you how to represent in n dimension at least. So, what we can do is we for each vertex v of the vertex set of G, we construct an interval graph I v like this. So, we associate an interval for v, and then v has some neighbors, let us say n of v, and v has some non neighbors n bar of v's, let us say this is the entire vertex set, total v union n of v union n bar of v will give you the total vertex set, right. Now, so if this is v, now all the neighbors of v can be placed here, right. See one on top of the other, because it's the same interval can be given to them like this touching v, and then so though I am drawing like this, it is all same interval like this, and then all the neighbors of n bar of v can be placed after that, maybe like this, right. N bar of v comes here, n of v comes here, and v comes here. This is an interval graph. This is now an interval graph, and you can easily check that this is an interval supergraph of G. Why is an interval supergraph of G? It is because if you take any edge x y in G, if both x and y are in the neighborhood of V, then they are intersecting here, right. And if one of them is V, then the other has to be in n of V, because they are an edge, and then they are intersecting, and then one of them is in both of them are outside n of n bar of V, then they are also intersecting here, and one of them is in n of V and one of them is in n bar of V, they are intersecting here, right. So, therefore, all the edges which are present in G is present. So, it is a super graph, there are more edges, that is the only thing. But as far as V is concerned, so this is what for each vertex we can draw a graph, we draw such n graphs, right. For each vertex I v, for each vertex v I can construct an I v like this. Now, I claim that if I take the intersection of all these interval graphs, I should get back the edge set of the original graph, because everything is a super set. So, when you take the intersection, we may get a superset. Is it possible that some edges which are not present in G may still remain in the intersection? Suppose such an edge is there x y, which is not present in E of G is present in the intersection. So, let us say for x and y, for corresponding to x, I have constructed a graph, right, like this. So, now where is y here? Y cannot be in this group, because y is in n bar of x, right, because it is not a neighbor of x. So, y should be in n bar of x. So, y is here, this is it. Now, you see here x and y are not intersecting. So, therefore, even x y is not an edge of this interval graph I x, is not an edge of I x. So, when you take the intersection of all these interval graphs, we should get back the original one. So, the key point here is one thing is we have we have shown that every edge which is present in E of G is present in all the graphs, because that is what is meant by saying that all these interval graphs are super graphs of G. Now, second, we have shown that whenever there is an edge missing in G x y say, it should be missing, it should be absent in one of the interval graphs we considered, which means that when we take the intersection of all these interval graphs, the original edge set will anyway remain in the intersection and nothing more will remain, because every extra edge, that means an absent edge in G will be absent in one of the interval graphs, and when you take the intersection, that has to disappear, right. So, that is the key point. So, this is the idea. So, what we have seen is there is always given a graph, it is always possible to represent the graph in n dimension. Why do I mean by say, I repeat that when I get n interval graphs such that the given graph is the intersection of these n interval graphs, it means that you can draw the corresponding box representation in n dimension by taking that each of the interval graph in different axes and reconstructing the boxes. How do you reconstruct the boxes? For instance, in 2 dimension, if you know the projection corresponding to x in x axis and the projection corresponding to y in x in y axis, then definitely we can draw the corresponding rectangle back, right. Then because the intersection will happen between the rectangles only when all the projections and all the axes are intersecting. So, therefore, essentially the edge set that results in the intersection graph corresponding to the boxes we draw will be essentially will correspond to the intersection of the interval graphs we considered. Therefore, it is enough to show that we can get so many interval graphs such that the given graph is the intersection graph of so many interval graphs. So, the key point here is anyway the idea is, given a graph, you can always find some value which is less than equal to n, such that it can be represented as the intersection graph of axis parallel rectangle in so many dimensions in a, so the boxes of that dimensional space. Now, Roberts had shown that in fact you need only n by 2, and extending the argument which we gave for this graph, right, this is the triangle this graph, extending the argument that we gave for this thing to say we can put n by 2 vertices here and n by 2 vertices here, and then we can put all the edges except a perfect matching here, all the edges except a perfect matching here. So, the this is exactly this graph. Instead of 3 vertices, we are taking n by 2 vertices here, n by 2 vertices here. We can argue that at least n by 2 interval graphs are required if I want to represent it as the intersection graph of so many interval graphs. So, therefore, he has shown that n by 2 is an upper bound for the number of dimensions required, and then for some of these graphs you need n by 2 also. And of course, the interesting question is what is the smallest value, and we also can call this parameter as Boxicity of the graph. That means the minimum integer, it is the minimum k such that G can be represented as the intersection graph of axis parallel rectangles in k dimensional space. So, the minimum integer k is that G can be represented as the intersection graph of some family of axis parallel k dimensional boxes is called the Boxicity of G. So, later in fact, many other upper bounds are known for Boxicity rather than n by 2. So, for instance, it can be shown that in fact 2 into chi of g square is an upper bound for the Boxicity, where g square is the square of the graph, square of g. Square means what? That means you take g, and along with that you add a few more edges. Whenever u and v are non-adjacent and at a distance of 2 in g, then we add this new edge. So the resulting graph is called g square. So this is chromatic number of g square times 2 will be an upper bound for Boxicity. This will be 2 times delta square plus 2. Easily you can easily show that this is at plus 2, and yeah, by some little work you can show that 2 delta square is also an upper bound. Later you can also show that it can be improved, but it is just for information's sake. But our point is to show that these are all generalizations of interval graphs in various ways. There are several other interval graphs, and these are all interesting special classes of graphs. So, like Boxicity, you can also consider intersection graph of axis parallel cubes. Say a cube in 2 dimension will be square. So, that means it is a restricted case of box representations. That means every box has to be of equal, so side length, right, equal side lengths, all different boxes. Each box has to be of a unit side length, let us say unit cubes. That then if I can ask the same question, what is the smallest integer k such that I can represent the graph G as the intersection graph of k dimensional axis parallel cubes. This parameter, the minimum integer, is called the cubicity. Cubicity is always greater than or equal to Boxicity because the cubes are a special restricted kind of boxes, and they can be somewhat bigger, sometimes even a log n factor bigger than box representation. And another parameter, similar parameter, is called sphericity, where we use spheres instead of boxes or cubes, and we are supposed to use some k dimensional spheres, right, instead of just 3 dimensional, or 2 dimensional sphere will be a circle, right. Again, coming back to 1 dimension, it will all become intervals. The cubes will become unit intervals, while spheres, right, in the again unit intervals. But we are, in the case of spheres, we have 2 options. One is we can allow spheres of same radius only, or we can allow spheres of different radius, and sphericity is used for the corresponding dimension when we allow only spheres of unit radius. So, these intersection graphs can have applications, like for instance, if you can consider a molecule, and then so the molecule is a graph, right, because when 2 atoms are close together they have some attraction, and then we can capture the molecule as a graph, like when 2 spheres around the nucleus, this force field, and then when they are close enough they will intersect, otherwise they will not intersect, right. So, this intersection graphs of spheres, right. So, anyway, so these are all to introduce some concepts which are related to interval graphs and generalizations of that, and essentially some very interesting special classes of intersection graphs. Now, with this thing we will leave this topic, because though there are a lot of material that we can study about this thing, but because we have other things to see in this lecture series. So, we will leave it to the interested student to explore these parameters in the leisure time. So, of course, there is a lot of material in the literature. And now we go to a different topic called the Hamiltonian circuits. In fact, we have seen a certain type of circuits earlier, which is known as the Euler circuits. So, what was that? Given a graph G, so you are taking a closed walk in such a way that every edge is covered once and only once, right. So, for instance, so if this is this thing, so this was the Euler 2, right. You just go from here and then go from here, maybe. So, you can go like this. So, we had studied it earlier. So, if you go like this, you have covered every edge exactly once. Now, the Hamiltonian circuit is its Hamiltonian cycle is a counter is a the corresponding question for vertices. So, given a graph G, so we are interested in a closed walk such that we meet each vertex once and only once. So, it should be like this. So, there can be several. So, we should come back to the original place, but in our walk, in our circuit, we should meet each vertex of the graph exactly once, right. So, sometimes such circuits may be there, sometimes the circuits may not be there. For instance, let us see, do we have such a circuit in this graph? Here you can try to do this thing, because the problem is if you go like this, then if you get into this, you cannot see, you are meeting it for second time, right. Or if you do not start from here now, so if you go from here and then go, but then you will end up coming here. So, it is with some trial and error we can see that it is not possible to find a Hamiltonian circuit here, because every time you without re-entering the vertex, one of the vertices, you cannot come back to the same place, right. So, what are some obvious situations where Hamiltonian circuits cannot be present? For instance, the very fact that we are saying that every vertex should be visited once and only once, and we should come back to the place where we started. It means that the vertex, in the graph, each vertex should have a degree of at least 2, because the circuit should enter it and come out, right. Otherwise, we cannot have a Hamiltonian circuit. That means, the minimum degree of the graph should be at least 2, otherwise there is no way of hoping for a Hamiltonian circuit. So, a graph is called Hamiltonian graph if there is a Hamiltonian circuit in the graph. So, does it mean that if we increase the degree of the graph, you can get a Hamiltonian circuit always? That is also not correct. For instance, you can construct a graph like this. So, for instance, if you have n1 nodes here, n2 nodes here. So, every vertex here have degree n1 minus 1, right. So, here n2 can be bigger than n1. So, minimum degree of the graph, such a graph is, suppose if I make it a clique and if I make it a clique, if I both of them clique and then paste them on one vertex, it is a connected graph, but delta of g can be greater than or equal to n1 minus 1. So, there is no Hamiltonian circuit in this graph. Why is it so? Because at some point if you want to cover all the vertices, you have to cross from this side to this side, right. Then you cannot come back because there is a cut vertex here, we cannot come back. So, if there is a cut vertex, then we cannot have a Hamiltonian cycle, because two connectivity is a requirement to have a Hamiltonian circuit in the graph. So, it is not possible to have Hamiltonian circuit in a graph when there is a cut vertex. So, it says that even if we try to keep the minimum degree as much as possible, to a great extent you cannot achieve a Hamiltonian circuit in the graph just by that assumption. So, the worst case may come, for instance, from this example, the worst case may come when we consider an n by 2 seal sized clique and then an n by 2 sized seal size clique here, because you know this is a common vertex. So, we have if n is an odd number, so n minus 1 by 2 special exclusive vertices here, n minus 1 by 2 exclusive vertices here, and then one extra, right, that will make it. So, that means even so then the minimum degree of this graph will be n minus 1 by 2, right. So, n by 2 floor, even then we see that it is not allowing us to have a Hamiltonian cycle, because there is a cut vertex, because to avoid the cut vertex it is not enough to have the degree high, minimum degree high, minimum degree has to be very really high, then only it can go to the level that it can guarantee that there are no cut vertices, right. This example will tell that the minimum degree is, even if minimum degree goes to this level, right, it is not. But then very interestingly, if the minimum degree is above this, for instance, if we know that minimum degree is greater than or equal to n by 2, then the G is Hamiltonian. This is the first theorem we want to study in this section. For G, if minimum degree is greater than or equal to n by 2, then G is Hamiltonian. And also of course, so that is not just enough, because if G has just 2 vertices, it cannot have Hamiltonian cycles, right. So, we will say that if the number of vertices is greater than or equal to 3 and the minimum degree is greater than or equal to n by 2, then it has a Hamiltonian cycle. The technique to prove this is like we have already encountered this kind of ideas before. So, again this proof is from Dirac. So, what we consider is a longest path in the graph. So, we consider a longest path in the graph. So, but when we see a longest path, the interesting thing is that all the neighbors of these endpoints has to be on the path. Suppose the longest path has some k vertices in it, k can be less than or equal to n, it can be strictly less than n also, right. Suppose the longest path has some k vertices in it. So, let us say or maybe say k plus 1 vertex in that, so let us mark it as u0, u1, u2. So, this is uk. Now, what can I tell about the neighbors of uk? The uk's neighbors are all in this collection, right, because it cannot have a neighbor outside. By this, suppose if you have a neighbor outside, this collection, then this cannot be longest path. It will, you can extend the path from here to this node also, right. So, it cannot be a longest path. So, therefore, it is not possible to have a neighbor outside this. So, this neighbors of UK are all inside. Maybe it can be like this, it can be like this, it can be like this. Okay. But we know that UK has n by 2 neighbors. So, this green edges that I have drawn from here goes to n by 2 of these places, which immediately says that this has to be some n by 2 right, n by 2 floor plus 1 more than this thing, suppose, right. I cannot say, because if it is an even number, n by 2 plus 1 vertices, k should be at k, okay, u0 also should be there, n by 2 at least, right. So, the neighbors of UK, n by 2 neighbors of UK has to be present somewhere here. And now it can be here. Now, suppose I consider the places. So, I identify the neighbors of UK here, and then I am just interested in the vertices just above each of this neighbor. See these vertices. So, I marked it green, right. So, how many such vertices are there? Okay, for each neighbor of UK, I identify one neighbor which is just above it. So, at least n by 2, right, n by 2 or more, because there are n by 2 neighbors here, and each of them, see, it does not mean that we are not saying that there will not be a green edge from here, but we are just collecting those vertices which are just up. So, if there is this thing, we will collect this also, not only this vertex, we will also collect the next vertex also, these 2 vertices I will collect, right. So, I am collecting all the vertices which are just after a neighbor of UK, and there are at least n by 2 or more such things. Now, the question is, where are U0's neighbors? So, is it possible to have U0's all neighbors are in this collection of case U1 to UK, among the U1 to UK, all the neighbors of U0 should be present. Now, is it possible for U0's neighbors to avoid all these places which are just above the neighbors of just after the neighbors of UK? In that case, because we have already considered at least n by 2 such positions, right, and U0 is one, U0 itself cannot be a neighbor of that, right. So, this k can be maximum n minus 1, right. So, sorry, n. So, then U1 to UK can be total n minus 1. So, among the available n minus 1 positions, if you avoid n by 2 or more things, then you will have only less than n by 2 candidates for then placing the neighbors of U0, right. We cannot do that, because U0 also have n by 2 neighbors. So, it is clear that it is not possible for U0's neighbors to avoid all these places, dark green places which I have marked, means the places which is just after a neighbor of UK. Repeating the argument. So, we considered a longest path. The interesting thing about the longest path is both U0 and UK, the n vertices, should have its neighbors in this path itself. We claim that there exists a neighbor of UK in the path such that just after this, the next vertex in the path is a neighbor of U0, like this. There is something like this is what we mean. Suppose it is not there, then U0's neighbors should be avoiding all these places which are just after the neighbors of UK, right. That means they are avoiding greater than or equal to n by 2 places from the n minus 1 available places for them. So, how many of them can be there u0, how many neighbors u0 can have? Only at most n minus 1 minus n by 2, that is strictly less than n by 2, but we know that u0 has at least n by 2 neighbors. So, it is always, it is guaranteed that u0, at least one neighbor of u0 will sit just after a neighbor of UK, some neighbor of UK on the path. So, this clearly tells us that this path can be converted into a corresponding cycle this way. So, for instance, if I draw it with green, so I can go like this, then I can take this jump to UK and then come back and then take this jump back to u0. The green cycle which I have drawn here will be a cycle of length k, right. Sorry, k plus 1 here. So, means if the number of vertices in the path is k plus 1, here the cycle also has the same length. So, that path is converted to a cycle now containing all the vertices, right. That was possible because we could identify an edge in the path such that below the earlier n vertex of the edge with respect to this path was a neighbor of UK and the other n vertex was a neighbor of UK. That is why we could cut it here, right. So, that is why we could make it. So, we just get rid of this thing, we get a cycle like this. Now, if this u0 to UK was the entire set of vertices, that means this path contained all the vertices, we are done, we got a Hamiltonian path here, cycle itself here. So, suppose it is not, then there should be some vertex outside the graph, there should be some vertex outside the graph, outside this cycle in the graph, such that it is not part of this, but then this is a connected graph. So, this cycle cannot be totally disjoint from the remaining part of the graph. So, if there are some, there should be some vertex outside which is adjacent to something here in the cycle, right. So, maybe it is adjacent to here, say it is adjacent to here, right. It has to be because it is a connected graph, you cannot have this cycle not adjacent to any vertex in the remaining graph. In that case, what will we do? We will start from, because here suppose if this is the this thing, so then consider the vertex which is just below the cycle. We could have started from here, followed this cycle like this and then followed here, and then we could have extended it, because it is a cycle, any vertex adjacent to the cycle can be brought into a path which contains all the vertices of the cycle and that, because we can jump into this and then follow the cycle like in whatever order until here, right, and then we will just cut here, that is all. So, so this will be a longer path, because now it contains more vertices, see u0 to UK and this vertex. So, the original path we considered was not the longest path. So, it is a contradiction. So, we can infer that. So, if the minimum degree of the graph is greater than equal to n by 2, then we should have a Hamiltonian cycle in the graph. So, the crux of the argument is to consider the longest path, and then we argued that the longest path can be converted to a cycle containing all those vertices in the path, and if this longest path contained all the vertices of the graph, then we got a Hamiltonian cycle, because now one cycle has all the vertices in it. If not, then there should be some vertices outside this cycle which is adjacent to at least one of this vertices of the cycle, otherwise the graph will get disconnected, right. Graph is a connected graph. Why is it a connected graph? Because the minimum degree is n by 2, and you cannot have a graph with minimum degree n by 2, but disconnect it. What is the reason for that? The reason for that is, suppose it is disconnected, there should be a smallest component. The smallest component will have number of vertices less than equal to n by 2, and even if it is a clique, the degree of the vertex has to be strictly less than the cardinality of the component less than n by 2. So, it follows that it cannot be disconnected, right, it cannot be disconnected. So, therefore, the connectivity is assured. Therefore, every vertex outside the cycle has to be adjacent to at least one vertex on the cycle, and we can cut the cycle at that point and elongate the path, make the path longer, right. That contradicts the assumption that we have taken the longest path in the first place. So, now let us look at the situation. So, is it possible that it is the connectivity that creates the problem, because we have seen that an example where even n by 2 floor minimum degree of n by 2 floor is not helping us to infer that there is a Hamiltonian circuit in the graph. So, but then there was a cut vertex, that was the problem. Suppose we assume that the connectivity of the graph kappa is greater, can it help? For instance, is it some 2, 3, maybe little high, it is a large value, but even then it will not help, because if you consider a complete bipartite graph. So, let there be n1 vertices here, n2 vertices here. So, it is a complete bipartite graph. The connectivity of this graph is definitely n1, because you can see any 2 vertices if you want to disconnect. So, you have to remove all the vertices here, because as long as even one vertex is left on the other side, then you have a path still through that vertex, right. So, the smaller of the two parts is the connectivity of this complete bipartite graph, right. So, then what you can say is how big a Hamiltonian how big a cycle can be there in this graph. Is it possible to have a Hamiltonian cycle? So, with some thought we can easily see that it is not possible, because so if you go, so any cycle can have to zigzag between the two parts, because the edges are only across the two parts. So, suppose if you go like this, then you can come here, then you go here, come here, go here, like this, you can zigzag between the two parts, but it is like the cycle is taking, every time it is taking one vertex from this side, it is taking one vertex from this side also, and then it takes one vertex from this side and one vertex from this side. So, it is finishing of the vertices on both sides in equal amounts. So, definitely n1 is, since n1 is smaller than n2, n1 will finish off faster than n2, and then we will not be able to follow the cycle, right. So, the cycle cannot be bigger than 2 times n1, right. So, that is finally when you finish this thing, you will have to come back here and finish. So, because 2 n1 may be the biggest cycle that is possible. So, you cannot zigzag more than n1 times, because every time it comes into this side, A side, it will this is A side and this is B side, it will finish off one more vertex from the A side. So, the connectivity cannot help, because this complete bipartite graphs have indeed high connectivity, but still it is not allowing us to infer that there are Hamiltonian paths in it. So, connectivity is also not the key thing. So, but there is interestingly, suppose you can assume that if you can assume that the largest independent set size alpha of g is less than equal to some number, say some t, then we can show that there has to be a large cycle in the graph, like you can show that there should be an n by t sized easily you can show that cycle in the graph. How do you show that? Because alpha is less than equal to t, what should be the chromatic number? Chromatic number has to be greater than or equal to say n by alpha, right, because any color class can have at most alpha number of vertices in it, t number of vertices in it. So, so there should be at least n by alpha, n by t color classes. So, the chromatic number has to be at least n by t. And now we had studied earlier that if the chromatic number of a graph is some n by t, then there should be a critical graph, color critical graph, such that this subgraph has chromatic number minimum degree is greater than or equal to chromatic number minus 1, here n by t minus 1. Now, again taking the longest path argument, if you consider the longest path in that subgraph, then we know that in the the longest path should have all the, see for instance, if you look from this side, so all the neighbors of it should be on this path, right, because otherwise you can make the path longer than this. Now, if you consider the last neighbor among this thing, so this entire part should contain n by t minus 1 neighbors of this thing, maybe more, but at least those many, and this vertex, that is plus 1, that is n by t vertices in it. And here we have because we can jump directly to here and then come back here via this. So, there is a cycle of having n by t vertices, right. So, therefore, we can infer that if the independence, biggest independent set size, if alpha is less than equal to t, then there exists n by t cycle in G. There exists an n by t length cycle in G, but it is not a Hamiltonian cycle, it is only a long peak cycle. It is because the Hamiltonian cycle means it has to be of length n itself, that means it has to contain all the vertices of G, all the vertices of G. Interestingly, so this is alpha being small is not enough to have a Hamiltonian cycle, but suppose the alpha is less than the connectivity of the graph kappa of G, connectivity of the graph, then we can infer that there is a Hamiltonian path. So, we will, the next aim of this aim is to prove that. How do I show that? So, now the setting is like this. Suppose you have a, so you consider the longest cycle this time, longest cycle this in the graph. If it is a Hamiltonian cycle, well and good, we are done. So, it is not a Hamiltonian cycle. Now, there are some vertices outside, right, the cycle, longest cycle. Now, we can consider to this cycle, we can consider a fan, because it is a k connected graph, right. There is a fan, k fan in fact. So, if for instance, if the cycle length is more than k, we can find k paths, independent paths starting from here, but internally disjoint paths and ending at different vertices here somehow, right. So, where it ends we have to analyze. On the other hand, if the cycle was smaller than k, then what will happen? Suppose it was a small cycle, very small cycle compared to k, then what will happen is you will be able to get fan paths starting from here to here to here to here to here, and reaching all the different n vertices, reaching all the different n vertices, right. That means the cardinality of the fan will be C. So, therefore, we can see that starting from any vertex outside, x outside, we will be able to identify fan paths of cardinality minimum of C comma k, where k is the connectivity of it, right, the fans. But is it possible that C is the smaller of k? No, because in that case what will happen, because this all to all vertices of V there is a fan path ending. Then what will I do? Then I will start from here, then I will follow like this and then come here and then go here and then catch this x and come back. So, this is a longer cycle than the red cycle, which I assumed was the longest cycle available in the graph. So, it is not possible to have this picture. That means there are so many fan paths coming from x and ending at all the different vertices of this thing. That is not possible, because in that case I can elongate so the cycle, can make the cycle bigger by not going through this edge, but go here and come back. It will be bigger, at least one more vertex. You may catch even more, right. So, it is not minimum of C comma k. In fact, C is bigger than k. In fact, we know that C is bigger than k. So, therefore, the k is the smaller of this thing. So, it is all the k paths should be there, but is C so small compared to k? Definitely not, because as this argument we just told essentially tells us that we cannot have two fan paths from x ending at adjacent vertices of C. So, because we can, if this is ending here, then we cannot have an ending here, cannot have it ending here. So, it can only end here, right, from next, because otherwise we will just elongate here, right. And we will continue with this proof in the next class, because this needs some time. So, we will finish it in the next class. So, thank you.